Hi class. This lecture I'm going to talk about a few topics such as references, pointer, and memory access. Um, this is for both the C language, also some part of that for C++ language. So we're going to cover some of the issue which that will be useful for both programming in C or C++. So just a reminder that we're still in this cluster of chapter 13, 14, and also chapter 6. And then we're working on the homework assignment number 3. So for this, I will start with this slide. So this is a typical computer motherboard with CPU, with memory, with everything. That this is the hardware platform that we're going to execute our program. And one of the things that's really interesting is that when I create an object or create a variable, it's going to be stored somewhere. I mean, for example, homework assignment number 3, it might be hosted in your local computer, but it might be a similar motherboard in a data center somewhere else on the internet. And so there's one thing about where is the object that is very important, which you already start to realize the mechanism and application during the development of homework assignment number 3. But the other thing is also very interesting is that even just with one machine, when I say I want to allocate memory space for an object, for a C++ object, then do I know where I actually put that object? For example, in the hardware, which memory bank or whether this touched the cache memory or this is touched on some other peripheral device, and where is the flow of the object, where exactly my object really is in this hardware. It's interesting, most of the programming language doesn't allow you to access that kind of information. And C and C++ is an exception. In fact, it's so interesting, my knowledge that C and C++ is the only high level programming language that allow me to do such kind of low level access like what you're seeing on this slide. So we're going to look at, well, how do we handle that? This is what we call memory layout, memory access, which is related to the way C or C++ present the concept of pointer, address, reference, and a bunch of other mechanisms which put together allow us to really fully utilize not just a feel about a high-level programming language, but also have the capability to access something normally only assembly language can access. So I'm going to talk about address. So for homework assignment number 3, we need to store the distance, which is the double, which represent the miles between, say, New York and Davis or New York and Sydney. So we have the need to store this double number, but the thing is that where exactly this number is being placed on my computer and which area it has. And for some application that this is totally irrelevant. I don't care where it is. You just store me a number, I want to use it. But for some application that this capability is critical, especially for embedded system when the system need to touch some hardware mechanism, and that capability is important. And therefore, for me to even describe what that really is, we need a concept called address. Means that I need to know where it is, then I need to have a way to specify the address of that location. And so in this talk, when I say address, I really mean memory address. So for example, when you use the scanf function, that this is, I mean, of course, right now in C++, you use C in and C out. But in the C language, that was a format string that you can actually write this piece of code. You try to input this number, miles, which is a double, and put into that memory. So in this sense, I have to tell my system where exactly I want that number to be stored. So that introduced this M sign that's shown in the first line. So when I put a variable, when you declare a variable, in this case, this variable miles is a double, which means that in C language or in C++, a double is 8-byte storage. There is 8-byte memory I need to have in order for me to store the number double. So most other programming language, that's the only thing you need to do. You just specify 8 bytes, and then that's everything you need to worry about. It will be stored. You don't know where exactly it is, but the number of the double will be placed in that location, and you will be able to retrieve that. That's great. But C actually offer you an even lower level representation about that information. So not only I tell you abstractively, there is a variable called miles. It can store a double, but I further tell you what exactly is the memory address of those 8 bytes. So, for example, in this example, miles actually store in this 8 bytes starting with 7014 AE00. That's the address of the first byte. And from this first byte to the next until 7014 AE07, those 8 bytes together are allocated to store this double. And usually when you put an M sign before the variable, that's essentially saying the address of the first byte of the variable. So this variable right now is 8 bytes, but this variable could be only have 2 bytes or 4 bytes, or even have 200 bytes. If this is an object, this is a big one. And therefore, this M sign is providing you the address about where this storage exactly is. C and C++ gave you that capability for you to do that. Okay, so this actually comes to the important idea for programmer for C and C++ is called memory box. So essentially what we deal with is not just a regular programming about having variable, having control flow, having class definition, having inheritance, but also we have the concept called memory box. Means that every single memory byte in your memory is addressable by the address. So what I showed you earlier is just 8 different bytes. They can actually put it together. I do want to mention that you can use the size of operator to find out what is the size of that particular type. Either is a basic data type or is actually a more complicated, such as a structure type or a class type. You're okay to use size up to actually figure out how many bytes they have. For example, in this slide, I show you a integer on not all the computer, but at least on the computer I was using. Integer is 4 byte, floating point is 4 byte, double is 8 byte, and character is 1 byte. You can use size up to actually get those. So if you look at the memory box information, when we want to store that miles, it basically takes 8 bytes, just like this. It's somewhere in the total memory that you have is being placed. And the thing is that this is important if you look at the slides. I mean, I'm not going to spend too much time to explain this. This is essentially the whole memory map about a program that you want to run on a typical Ubuntu or Mac OS, this kind of environment that is specified not just about every single byte is addressable, has an address, but it actually separates, saying that, well, if you're doing malloc or delete, or you're doing new and those kind of operator, where's the address the memory is going to put into? If you have some static variable, where I'm going to put it. So essentially that memory address allow us not only to be able to see where they are, but we can control and manage. That's why this memory address awareness is a special feature, not useful all the time, but there are some application that needs this kind of capability to gain quite a bit of functionality. Okay, so now I'm going to having the idea about the ampersand. Now I'm going to extend it a little bit to look at the representation. How do you define from the address to a pointer and to a bunch of other language construct? This might be just a review for you. You probably saw this already on ECF 36A. So to declare a pointer, usually there's a type, and then there's a star, and then there's a variable name. So for example, if you have an integer x, which is x means x is an integer, and type is integer, and then now you can do the second line integer star xp, which means xp the type is integer star, means that it's a pointer to an integer. And then you can actually using this xp to store an address. So you can have that x variable, put an m sign. Mx means that it's an address. And you put that address and store in the xp. So in some sense, when I say xp is a pointer, I'm actually let it store the address. So which means that address and pointer in C are the same. Okay, so this is important because based on this, there's another thing is the same, is xp, which is a pointer, address, which is a memory reference, and it's an integer. It's an unsigned integer or unsigned long integer, depending on whether you're having a 32-bit address or 64-bit address. So those three concepts, they are similar. They're powerful for their equivalence, but also they're a bit tricky to handle when you think about mixing number, address, and the pointer together. So the example I gave you looks like this. For example, XP. The XP itself has this picture. It looks like, I'm assuming you have a 32-bit architecture. So XP itself is a 32-bit integer, which I use that 32-bit integer to store an address. So that's why the 4 byte that XP has, the first byte is 034 EF5D00. That's the address of that XP as a variable. But then the variable x itself, okay, so xp is a variable, x is also a variable. Each variable needs 4 bytes. That's why x actually also have a 4 bytes, started with 0x34EF5F12. Okay, so there are two regions, two 4 bytes, but this first 4 byte is allocated for xp, and the second 4 byte is allocated for x itself. So when we execute the third statement, we put xp is equal to mx, and that statement essentially put x address, which is the first byte of that orange integer. Right now the value is 222. The first byte's address is 0x34EF5F12. I'm actually storing that value into that yellow 4 bytes. So essentially XP has its own address. The content is also an address for another integer. So that's what we're implementing between the X, XP, and MX. I hope that in this picture, and if you are not familiar with the concept of pointer and address, that this picture is important for you to know which one is which. Where is MX? Where is XP? Where is MXP? And where is a star X? And those four things, if you look at this graph, and then you will learn exactly about how the pointer and address is doing. So let me actually just repeat very quickly. Where's MXP? MXP is actually 0x34EF5D00 because M means address. And the address of XP itself is the number I just read to you. And what's XP? XP is the content of that address. So the content of XP is 34EF5F12. And what is X? X is 222. That's a value. And what is MX? MX is 0x34EF5F12. So which means that MX is equal to the content of XP, which is exactly the result of the assignment we just showed you. Okay, so this hopefully conclude that everything about the representation between pointer, address, and how do you hook them together like this. Okay, now I'm going to move on to the next scenario about memory address. And so very popular that we need to use all kind of array. One-dimensional array, two-dimensional array, or in this picture, I have a three-dimensional array. So conceptually, our program, depending on how many dimensionality you need for your application, you will design an array like this. For example, this case is a three-dimensional array for 3D array. Okay, however, we also need to worry about how this array are being referenced and being represented in the memory. Because remember, we have this memory cell model. So I do want to say that why this is related to the address and pointer. So when we talk about address and pointer, we really talk about an address is a pointer. It's also an unsigned integer, 32-bit or 64-bit. In fact, there is a fourth element that an array is also a pointer. An array is also an address. If you think about how this array being stored somewhere in your memory. So usually there is a very interesting way about how to represent an array element using the pointer notation. For example, at the end of this slide toward the button, you can see that the way for me to represent, usually this is a two-dimensional array. I have an array called M. Then I provide two indices, X and Y. And this is in C, this is equivalent to star M plus X times the number of columns of that two-dimensional array plus Y. And the left and right, they're equivalent in terms of representing. So this is just representing that how you can also interchangeably between the array access and address or pointer access as well. Okay, why is this important? So I want to show you the next one. The next one is the top. I show you an example about a two-dimensional array, 4x4, right? You have this 4x4, and then you can actually give a M sign on this 4x4 array, or you can get an M sign on the first element of this array, which is a 0 and 0. So here is one concept I should let you know, and this is important, very fundamental, very useful, is that when we represent array in the memory box, we have addressable space from the top to the bottom, and therefore is a one-dimensional array. So essentially, any higher dimensional array need to go through a process which we call linearization, and such that we convert that two-dimensional array into a one-dimensional array like here. So essentially, even though conceptually you got a 2x2, 4x4 array on the top, in memory box model, everything is just linearized over there in the button. And therefore, based on this linear model, that you can use that pointer address formula I showed you in the previous slide, but also in this slide to do that reference. Okay, so essentially every single array, regardless how many dimensionality, that you will be able to just construct using linear array, also with some other information I will be able to access. In fact, in the lower level implementation of array in C language, it's actually the pointer notation that's actually being really operate here. Okay, so that is the idea about doing array representation using the pointer and memory address. And this slide, I just want to show you that sometimes the representation depend on the size of the element in the array. So I was showing you the idea about either the size of character. If it's a character array, then size of character is 1, so you times by 1. But if this is an integer array, then size of integer is depending on 4, you times 4. Okay, so that is the formula you need to add the size of. So if you want to do this kind of calculation, you have to use the function size of appropriately. Okay. With this representation, now I'm going to show you an example. So this example, I won't explain too much because I really want you to try to run this program and get the result yourself. Okay, so this is a two-dimensional array. This is two-dimensional array. I make it to be linear on the button. Okay, so in this piece of code, I make this array instead of 4x4, I make a 2048 by 2048, which is a pretty big size array. And I try to copy this array from one to the other. So you can think about this could be very useful in a copy constructor, which whenever somebody wants you to copy a new big object, it is a 2048 by 2048 array, and then you're going to do the copying. Okay, and then I give you two pieces of code. One is called copy ij, one is called copy ji. By the way, this piece of code was developed from a CS course in Carnegie Mellon University, which I think is a great example about how programmers need to be aware about the memory layout, and then they will be able to write the optimized code to actually make the performance a lot better. Okay, so the performance awareness is always desirable, especially with this kind of language like C. Okay, so copy ij and copy ji, they are extremely similar. They're extremely similar, except the way they access this double loop, I loop and j loop. They're actually just turn around. Instead of going I go j, or go j first, go I. And the thing is that with this two different logic compound with this linear representation about the array, and I want to tell you that one of the function, even though you're copying exactly the same two-dimensional array, that one of the function will run a lot faster than the other. In my experiment, it's about 6 times faster. Some of the people write the same code, they do experiment, and they accomplish almost 20 times faster. One of them is faster than the other. So I'm not going to tell you which one is which, but I want you to run this program and find out yourself to see which one is faster, and then think about why it is faster. Okay? That's your homework assignment number 4, by the way. All right, so now I just want to summarize what we have done so far. So we talk about the memory box model or memory cell model with a different data type. So we mix a few concepts together. We have the address, we have the pointer, we also have the array, and they can be interchangeably to represent one another. And also, on top of that, this number is a unsigned 32-bit integer or 64-bit integer, depending on the architecture. So this is really interesting that we have so many things that kind of confusing us, but also provide us some flexibility to do something quite powerful. All right, so the other thing I do want to mention is that with this memory layout, then we need to think about how to allocate the memory, how to release the memory. So you probably already heard about malloc and free, which is help us to allocate a chunk of memory, and then the return is an address of the first byte. So for example, this example that XP is a pointer, a generic pointer, and malloc, you have to tell the malloc library to say how many memory bytes I need to allocate. And by the way, here is a structured data type called planet type. And size of planet type, whatever it is, how many bytes, that the malloc is going to give you a chunk of memory that's enough to store a copy of the planet T. And then the address to the first byte will be returned to XP. So XP will be storing a pointer pointing to this particular structure. So again, you see we're using the concept pointer, address, and also the size of the data type we need to allocate. And of course, important thing here is that in malloc, it needs to pair with free. So whenever somebody is malloc something, at some point you need to free the memory. If you forgot to free, if the system keep running, you're going to have something we call memory leak. Means that you're going to eventually use up all your precious memory, and the program will die in that case. Okay, and this is also similar to the C++ constructor, destructor, new, and the delete. And those two are essentially correspond to malloc and free, as I mentioned earlier. So one of the things that we will cover later, which as we're in chapter 6, I kind of give you a heads up, is that chapter 6, there's a new topic called smart pointer. So in the pointer, you need to worry about malloc and free. But smart pointer has this smartness such that when you malloc, as long as you don't have any reference to that pointer, and that memory will be automatically give back to the system. So this will avoid a large chunk of error that the C and C++ programmer tend to commit, and which greatly improve the performance. So we'll talk about the concept of smart pointer. It's a great mechanism to reduce error. It does have overhead that you need to carry as well. Okay, so I want to actually go in to look at the planet T a little bit closely. Okay, so here is a definition of planet T, and you can see that it has a bunch of variable. It has name, which is I decide it should be 10 character, and then has a diameter, which is a double, has a moon is an integer, has a orbit time, which is also a double, and rotation time is double as well. So if you add this number together, you should get 38. But if you do size of planet T, you got 40. So there is a small difference between why I look at this memory, it should be 38, why you're giving me 40. And the reason is that all the memory allocation need to be word alignment. So in a 32-bit computer, a word is 32-bit. That means you have to have, everything has to be 4 byte. And so in this case, even though the name character string is only 10 bytes, but because the 4 byte alignment, I need to make it to be divisible by 4, so which means that one become 12. And therefore, the total size of planet T will be 40, and what you call malloc is going to return the first byte of the address for the 40 byte when you have the malloc. Okay, and essentially this 40 byte is in the memory cell model, what looks like exactly like this, which is a chunk of memory that's represent one object called planet T, and then it has all the memory space. You just allocate your memory. And the other thing which is important, they are contiguous. They're actually just put together that memory, and then you know how to do that. For example, you want to do a file copy, you just copy this 40 byte to the hard disk, or copy this 40 byte to the network directly, and then you can actually process this object very easily. Okay, so now we're done with the C part about the pointer and reference. Now I'm going to talk a little bit about C++. And of course, in C++, we're not doing structure anymore. We're doing class. So instead of doing struct planet T, then we have a class planet. In the class planet, we have a constructor, and we have a name, we have a diameter, we have a moon, we have orbit time, we have rotation time. And it's exactly the same. We can use size of to see what is the size of the planet. It's probably close to 40 byte as well, because it's being defined very similar. By the way, the C++ class, without the new additions such as the virtual function or inheritance, is very similar to the struct that we have in C. Okay, so their memory layout is quite similar as well in that sense. Okay, and now we're getting something which is tricky, is that because now we're in chapter 13, 14, we're talking about inheritance. And the memory layout for inheritance is fairly interesting. It's fairly different from the C. That's why I want to specifically emphasize this. So in C++, in fact, we have 3 types of inheritance. So far you have dealing with, I only talk about single inheritance, and I haven't talked about multiple inheritance. And I never talk about what do we mean by virtual inheritance. And today I'm going to give you your first example about anything other than single inheritance and comparison. What's the difference between multiple inheritance and virtual inheritance? So this is what we have for homework assignment number 3, and you can see that this is very nice, clean. Is a single inheritance with every class has at most one base class. Okay, have at most base class. And based on that, I can actually construct my memory layout, which is the same thing as my the memory box model I present you earlier. So for example, if I want to create a shadow person, you can imagine that the shadow person has a memory bytes that store the shadow person object, but then the shadow person also inherit from person, and therefore it has the person object as well, and the person inherit from core, so it has a core object as well. So your memory should be core object and then person object and then shadow object all together, and they should be contiguous together. And then when you do new on a shadow person object, that the pointer get back to you is essentially the address of the first byte of these 3 things together. So now I'm saying that when you have inheritance, the first byte is not for this particular object that we're just create, is actually first byte of the most base class, which is the root, which is the core, and the memory should be continued together because the compiler knows how big is core, how big is the shadow, how big is a person, so they can easily move the offset to access the variable of the class shadow person, the class person, and the class port using this memory model. So this is what we have been doing in the homework assignment number 3, and everything is about single inheritance and it's about memory layout. Okay, and now I want you to take a look at this program. So this is the program about multiple inheritance. This is a program that has 4 different classes: account, employee, student, and work study. Employee inherit from account, and student also inherit from account. And then work study is doing a multiple inheritance, so inherit simultaneously from employee and student. So that's the class hierarchy is with a multiple inheritance. So when you first take a look at this, you look at the layout, and you might think, okay, some of you probably already think the other option. You might think that their relationship looks like this, which is work study inherit from simultaneously from employee and student, and both of them inherit from account. It looks like this kind of inheritance relationship. Okay, for this example, when I draw the picture, it looks like this. This is not only represent the inheritance relationship, it also represents the memory layout relationship, and which is very important for us to know the difference between multiple inheritance and virtual inheritance. So in this case, when I inherit, just like earlier I mentioned, shadow person inherit from person, and the person inherit from core. And therefore, in my memory layout, the pointer to the object, shadow person, is actually pointing at the first byte of the core object. That's actually part of the shadow object, shadow person. So essentially, what is a memory layout in this case? If I look at this example, that I should have 4 memory region that put together continuously, because I have an account, I have an employee, I have a student, I have a work study. So essentially, I have a 4 object put together in this picture and somewhere in the memory representation, right? Well, however, there's another representation. Looks like this on the top. So this layout is, I separate that account into 2 branches. So essentially what I'm saying that the account object inherited by the employee object is a different account object that's inherited by the student. So essentially, I have a 2 memory layout in my memory for this object. And by the way, if you understand the memory layout perspective, I mean how many bytes you need to host this object, you know there is possibility of the top one and the possibility of the bottom one. In fact, it depends on application about which one is more appropriate. I mean, for example, if the account represents a email account at UC Davis, then a work study student who is an employee or is a student, they certainly should have only 1 account. They shouldn't have a 1 email account. So it means that the account should only have a 1 copy. But on the other hand, if this account is different, the account is like a payroll account. And the thing is that employee has his own payroll account and the student have another payroll account. And these 2 accounts represent totally different application. And therefore, you need to have a 2 copy of account. So essentially, the language should allow us to specify that which case we're talking about. So by the way, I should tell you that the top way of representing is called multiple inheritance. So when we talk about multiple inheritance, we really talk about the top. And the bottom is called virtual inheritance. So this is the idea of multiple inheritance. If you do like the code I wrote on the left, and that's what you're going to get in terms of inheritance relationship. The critical difference is that that account object will have a two copy in your memory. One for the left branch, which is the employee, and one for the right branch of the student. Okay, so you have this for the multiple inheritance. Okay, okay. So what happened if you want to do on the button? The way that this two class, employee and student, will share the same copy of the account. And that's what we call virtual inheritance. And how do we specify the virtual inheritance? By introduce the keyword virtual. So you can see that in the code, now I add one extra keyword. Class employee, public column, public virtual account. So not only I said it's a public account, but I said it's a public virtual account. Whenever I say it's a public virtual account, this become a virtual base. And this become a virtual inheritance. And when you do this virtual inheritance, you will have this relationship, not just as an inheritance relationship, but also as a memory layout relationship. So now you learn something new today, probably, is that multiple inheritance in C++ it's not just about is a relationship. Is a relationship represent how do I use the design about how people implement the base class that I can easily extend it, but also it involve, especially with multiple inheritance, about what is the memory layout to support this inheritance relationship. Okay. So in fact, it's interesting. We have three different kind of inheritance. Single inheritance, I will show you, is the most simple one. And between multiple inheritance and virtual inheritance, because their account has one copy or two copy, it turned out their memory layout are quite different. Okay, so I'm not going to tell you precisely how they implement this different layout, but I want to show you an example how different they are. So I want two message to you is, number one, if you can avoid using multiple inheritance or virtual inheritance, you don't need to use that. But if you really want to use that or somebody else force you to do that, be careful that whether your memory layout is not affecting your correctness, okay? Because you'll be surprised how different the memory layout is between multiple inheritance and virtual inheritance. So let's first take a look at the multiple inheritance, which is the memory layout looks like this. So we can see that now we have now I have two accounts, so I call it account E and account S, but they are both account. I just wanted to say that one of the object is actually account E for employee object, and one is account S, that's for student object. So I have a two copy of the account. So the memory layout looks like this. So the first part is the account E. So it always go with the left. What do I mean by go the left? Because in the inheritance relationship, the class work study first introduce the class employee, then introduce class student. So class employee is the left hand side about that. So it's called left first. So first is account E, and then is employee. So just like a core object first, and then we have a person, we have a shadow. The root of the hierarchy always come first in the memory layout. So account E go first, and then employee, and then the account S, and then you go to the student, and then finally you have a work study. So essentially, you have this 5-element. The layout looks like this. They actually contiguous, put together. And the interesting part is that when you try to use pointer to pointing this object, you're going to see some difference. For example, if I have a pointer, which is a work study pointer, I basically have a variable. The type is pointer to work study. And when I assign this to work using malloc or using new, and the WSPTR, the address, will be the first byte of the account E, the first byte of the whole chunk of this file. Okay, so the first byte is going to pointing at, the WSPTR is going to pointing at the first byte of account E. And also, if you want to casting, here I show you an example of casting. You casting that pointer to an employee pointer, to a pointer to an employee object, and that casting will not change your pointer value. Your pointer still pointing at exactly the same location, account E. Okay, the reason is that you can see that account E, because employee also need account E, so that's no problem. They can have it. So anytime you want to pointing at a beginning of the object, regardless how you're going to do casting, that for work study, employee, and account E, pointing at the beginning of this memory chunk, first byte, is sufficient for you to do that. But that might not be true for the other side, which is the other branch of the other branch of the multiple inheritance, which is the student. So now I'm casting the pointer to the first byte of the whole chunk of 5 element to the pointer to student object. When I do that, the casting is going to move that pointer to the first byte of account S. So now you can see that because I'm doing multiple inheritance, then when you do casting, your memory address is going to move to the middle place, because now you're being converted to a student object. If you stay at the beginning, then it will be looks like you're employee object. So you have to move down to be treated as a student object. So essentially, if I have an object I created as a student, the memory layout will be exactly the same after you casting. In this case, the memory layout is going to be account and student if you create a student object. Here is exactly the same. You will see account S, and then you see the student. Exactly memory layout. So that casting make perfect sense. Okay, so far this is good. This is not as simple as single inheritance, but it makes sense. I know that during this casting time, I have to adjust my pointer in order to do certain thing. Okay, so far so good. Okay, so now I'm going to show you the most complicated case, which is the what we call the virtual inheritance. So the virtual inheritance have this. In fact, you can see that when multiple inheritance, I have 5 blocks of memory I need to put together. In virtual inheritance, I really only have 4 blocks because I don't have 2 accounts. I only have 1 account. But unfortunately, because I want to do things smart to implement this concept called virtual base, I'm actually going to use more block. In fact, I'm going to use 6 block instead of 4 block. I have 2 extra block I need to introduce in order to do that. I mean, this is almost like what we call the virtual base, virtual table, virtual function. They are all related to this kind of mechanism to allow us to do something more flexible, but then we can have to managing the information to stitching things back together. So let's take a look at the layout first. In fact, this layout is very different from the contiguous layout that we have seen for both single inheritance and the multiple inheritance. And this layout is different because it uses a lot of pointer. It's actually using pointer to redirect how to stitching things together, because essentially we have 2 paths and then we have only 1 copy of the account object. And how do I actually present both paths to preserve their semantics, and yet they will be pointing to the right place, so I no longer can use this contiguous chunk of memory because it won't work for virtual inheritance. And I have to use pointer almost like a linked list to hook them together. Okay, so let's take a look at this, the memory layout. So the first memory layout, the first element is actually a pointer to the virtual table. So virtual table is a separate place, which when we talk about virtual function, we will actually revisit this concept. So there is a data structure to keep a lot of information about how the object in this class, they should be used the right way. So there are information in another facility, another table called virtual table, for the whole class. So the first one is actually a pointer, 4 by 8 by, depending on the architecture. It's going to pointing to the virtual table, which will give you the offset information that you know where do you come back to start reading this particular object in this case. And the second element is the employee, which is correspond to the green. So I have the employee here. But the third element is, again, is a virtual pointer. It's also pointing to the virtual table and then come back. And the fourth element is the student, because this is the branch that you have two. You either go with the employee branch or you go with the student branch. And then you have, finally, you have this work study. And then finally, you have the account. Okay, so you have the memory layout with this 4-element employee, student, work study, and account. And you have a two virtual pointer that's actually helping you to access one of the paths. So the first virtual pointer is dealing with the left path, and the second virtual pointer is dealing with the right path, okay, which is the student path. So you can see that if I want to access the work study itself, I still access the first byte. If I want to access the employee start casting, if I cast my work study object to employee, I also started with the first byte because the left path is the primary path. So both work study and employee, they will go with the beginning, that first virtual pointer to allow me to access to, essentially I'm looking that pointer to access to employee, and then I will jump to the work study and jump to the account. Okay, and the third element is second pointer, and the second pointer is primarily for the casting for the student object. So if you have a student object that you come in, it will go to that virtual pointer. And so this, by the way, this access is very different from if you create an object as a student object, because if you create an object as a student object, you don't have a multiple inheritance, therefore you don't need to bother the virtual table. Okay, but now because you're virtual base, you have to do that. I take that back. Sorry. If you even doing single inheritance with virtual base, you will also see a vtable PTR as well. I haven't checked that, but I should probably check with a single inheritance. So this is for the if you want to access the student object. And finally, if you want to access only the account object, then you don't have to go through any of this two. You just directly to access the account. By the way, this is exactly the same as when you create an account object as an account object, not by one of the derived child. Then it will point out at the third entry. So you can see that with virtual inheritance, the number one, there is a few things. It's quite complicated. Number one, the memory layout have some extra facility you need to add in. The compiler will add it for you. Is about 2 pointer. And number two, they're not contiguous like single inheritance or multiple inheritance. Their memory is linked by the virtual pointer itself. And number three, that the casting behavior could be really complicated because when you're casting, the memory address have at least 3 possibility if you're doing inheritance with 2. So if you misunderstood the semantics of casting in a virtual inheritance and want to use the address inappropriately, and that will become some kind of problematic practice when you want to do that. Okay, so I just want to let you know that I'm not encourage student to do virtual inheritance unless you really know what you're doing. And sometimes if you can get single inheritance to work, just like our homework assignment number 3, great. You should just make inheritance simple and understandable. People won't confuse between the difference between multiple inheritance and virtual inheritance. And also, there is other advantage for the simplicity of the inheritance relationship. And multiple inheritance tends to create a lot of different scenario that you need to worry about, especially if you have a similar function, similar variable on both sides. And then you have to do the right naming, scoping in order to get the right semantics. Okay? All right, this is my first introduction to reference, pointer, and the memory. I hope you review a little bit about what you learned from ECF 36A and also start understand those concepts. What does that mean when they apply to your C++ context? Okay, I will see you tomorrow.